In this video, we'll look at Test 5 in the AP class for Fall 2013, and we'll look at the key. Question number 1. Projectile motion problems involve a horizontal component in which velocity is constant and the vertical component in which acceleration is constant. So this is A. Remember, AY would be equal to minus G, assuming that you've set your coordinate system up like this, and Vx is equal to Vx naught, because Ax is equal to 0 meters per second squared. And you can see that now that we've covered forces by the fact that the free body diagram would simply have a single force, weight, acting in the y direction and no forces along the x. So now we covered chapter 4. It makes it even easier to understand why that is. A projectile is fired by a mortar. At the top of the projectile's trajectory, which of the following statements is correct? The projectile's horizontal velocity is increasing. No, we just said that's not true. The projectile's resultant velocity is constant. No, the total velocity is not constant, it's accelerating. The projectile's vertical velocity is 0. This is true because at the very top, right here, the only component of the velocity is Vx naught. And if you're here, then you have a component Vx naught, plus you have some y component, so that your velocity vector is parallel to the path. So in that case, you would have a y component. But at the top, you have no y component to the velocity. On a velocity time graph, a horizontal straight line corresponds to, well, a horizontal straight line would be a line of slope 0. Slope is acceleration on a velocity time graph, and if that's 0, then there's no acceleration. So let's say that was, say, 10 meters per second, and you had a horizontal line, then your velocity would be 10 meters per second, and you would have 0 acceleration. It does not necessarily mean 0 velocity. It could, but it only says it's a horizontal straight line. It doesn't tell you that it's along the time axis. Number 4. A boy is riding in a wagon at a constant velocity. He throws a ball directly upward with respect to hand. Neglecting air resistance, how will the ball land? All frames moving at constant velocity are equivalent. It means the laws of physics are the same. Or put in other words, i.e., it is the same as a frame where the boy is at rest. So there's no difference between the boy being on a wagon moving at constant velocity and the boy sitting on the ground assuming that it's at rest. In fact, the earth is not at rest, it's moving, but it behaves as if. So when you throw the ball up, the ball comes straight back down in the boy's hand. There is no different. Motion is relative. There's no such thing as absolute motion. Now, if he was accelerating, then we would get a different answer. This is discussed in part in those movies called the frames of reference that I assigned. A particle moves along a circular path at constant speed. Its acceleration 0? False. It has acceleration. It has tangential acceleration equal to 0, but it has centripetal, which is not 0 because it's curved. This is found by the fact it's constant speed. That tells me that there's no tangential. The centripetal is because it's curved path. So acceleration 0? No. Its tangential acceleration is 0, but its centripetal acceleration non-zero? True. Number 6. Which of the following statements is true about uniform circular motion? Acceleration vector is tangent to the circle. No. In uniform circular motion, the only type of acceleration an object has is centripetal, and it's toward the center of the circle. So this gets back to the one right above it. V squared over R toward center of the circle. Acceleration vector is constant? No, it's not constant. For instance, if it's over here, the vector would point in a different direction. Acceleration vector is away from the center of the circle? No. Particle accelerates toward the center of the circle? Yes. So that's D. Problem number 7. An object can have a constant speed even if its velocity is changing. True. Example is uniform circular motion. You can have a ball going at 20 meters per second here, following a curved path. Over here it's going 20 meters per second. Same length, but not pointing in the same direction. An object can have zero velocity even when its acceleration is not zero. True. Ball going upward at top of its flight. So you throw a ball, the ball went up to some place up here. So originally you threw it, say, upwards at 10 meters per second. It eventually gets to where it's going 0 meters per second, but the acceleration is still minus g at all points, even at the top when it's not going with any velocity at all. A particle moving with a velocity directed toward the right may have an acceleration directed toward the left. True. So you could be moving to the right. You can have an acceleration toward the left, and you're slowing down because the acceleration points in the opposite direction of your velocity. Problem number 10. What is the magnitude of the acceleration of a speck of clay on the edge of a potter's wheel? There's a potter's wheel. Speck of clay. There's a radius. It gives me the diameter, which is 2 times the radius, and it says that that's 0.74 meters. It says that it's rotating, and it's rotating at 35 revolutions per minute. Your book chooses to call that a frequency. Some other people would call this an angular frequency rather than that. Bottom line is I need to convert that to a time. So time is equal to 1 over the frequency. So that's 1 over 35 rev per min. But that's 60 seconds per 1 minute. So the time when I put that in is 1.714 seconds. The radius is the diameter divided by 2. So 0.74 meters over 2. And I find that to be 0.37 meters. Velocity is equal to 2 pi r over t. And I know that the acceleration, centripetal, is equal to v squared over r. Plugging that in, I get 2 pi r over t squared. times 1 over r. So the centripetal acceleration is 4 pi squared r over t squared, which is 4 pi squared 0.37 meters divided by 1.714 seconds squared, which is approximately 4.97 meters per second squared. Now, you could have worked this problem using AC is equal to omega squared r, where omega is in radians per second and is known as the angular frequency. And you could have found that by taking that omega was equal to 2 pi f once you converted f into seconds. Okay, so it's equivalent. I didn't do that because your textbook doesn't cover that in this chapter, although I put it in your notes. Alright, that finishes this video. I'll pick up the next set of questions in the next video on the test.